Hi everyone, and I'd like to welcome you back to Educator.com. Our next lesson is going to be on RC circuits, or circuits that have resistors and capacitors in them. Our objectives are going to be to calculate equivalent capacitances for capacitors in both series and parallel configurations, describing how stored charge is divided between capacitors in parallel, determining the ratio of voltages for capacitors in series, and calculating the voltage or stored charge under steady state conditions for a capacitor connected to a circuit consisting of a battery and a resistor network, an RC circuit. So, to start with, capacitors in parallel. Remember that capacitors store charge on their plates, and therefore they're storing electrical energy in their electrical fields. Capacitors in parallel can be replaced with an equivalent capacitor, just like we could do that with resistors. So, if we take a look, capacitor is a symbol like that, two even lines. We'll give it a positive and negative side. It has a potential difference across it, Q1 on one side, and we would have negative Q1 on the other side. And if we were to see this in a parallel configuration, we could draw one capacitor here and one capacitor over here, where we have plus minus voltage right here. We'll call this C1. That'll be C2. And the voltage drop across both of them must be the same. And since we know that C equals Q over V, then Q equals CV. So Q1 equals C1V, and Q2 equals C2V. So if we want the equivalent capacitance is going to be the total charge, Q, divided by the total voltage, V. Our total charge is going to be Q1 plus Q2, so that's going to be Q1 plus Q2 over V. But Q1 is C1V, so that's going to be C1V, and Q2 is C2V, so C2V over V, and I can factor a V out, so that's V, C1 plus C2 divided by V, or just C1 plus C2. Or in short, for capacitors in parallel, to replace them with an equivalent capacitance, all you do is add the individual capacitances. So the equivalent capacitance formula is C1 plus C2, and you just keep on adding them for however many capacitors you happen to have in that parallel configuration. All right, capacitors in series. Well, the charge on the capacitors must be the same, so we can replace capacitors in series also with an equivalent capacitance. But now our diagram's going to look a little bit different. Here's our first capacitor, our second capacitor in series. I'll call this the voltage 1 across capacitor 1, and voltage 2 across capacitor 2. We'll label this capacitor 1, capacitor 2. And over here we must have charge Q1 positive, which means we have Q1 negative over here. And we have Q2 positive and Q2 negative. But what's important to note is if we pay attention here, that part of the capacitor, those plates, are isolated. Charge can't get on or off the plate. So if we have Q1 negative here, that must be equal to Q2 positive over here. The total charge is 0 in that region, therefore Q1 must equal Q2. All right, so to start our derivation to find how we get the formula for capacitors in series, the equivalent capacitance, C1 equals Q over V1. Therefore, V1 equals Q over C1. We could do the same thing for C2. C2 equals Q over V2. Therefore, V2 equals Q over C2. Now, the equivalent capacitance must be the charge divided by the total voltage. Therefore, the total voltage must be equal to Q over the equivalent capacitance. Well, the total voltage must be equal to V1 plus V2. So if we write V total equals V1 plus V2, I can replace V total with Q over C equivalent. V1, we just found out, is Q over C1, and V2 is Q over C2. Well, if I divide both sides by Q, what I then get is 1 over C equivalent is 1 over C1 plus 1 over C2, and that will go on and work for as many capacitors as you happen to have in series as well. So capacitors in series combine like resistors in parallel, and capacitors in parallel combine like resistors in series. Excuse me. And just like we did for resistors, for two capacitors in series, if you have just two, the equivalent capacitance is going to be C1 times C2 over C1 plus C2. But that only works for two capacitors. If you have more than that, you've got to go back to the general formula. All right, RC circuits are circuits comprised of a source of potential difference, a resistor network, and one or more capacitors. And we're going to look at RC circuits from the steady state perspective. We're going to look at what happens when we first turn them on, and we're going to look at them again after they've been on for a long, long time. And what we call a long time is a special definition when we're talking about circuits. The key to understanding RC circuit performance: uncharged capacitors act like wires. Charged capacitors act like open circuits. When it's fully charged, it can pretend it's open. When it's completely uncharged, it acts like a wire. This is the key to our entire analysis coming up. So, charging an RC circuit. Let's first draw an RC circuit where we'll start off with a battery with some terminal voltage, VT. We'll put a resistor here, R. We'll add a capacitor to our circuit, capacitor C, plus minus, the potential difference across it, VC, and we'll add a switch here. So here's our switch, and at time t equals 0, we're going to close the switch. Now initially that's uncharged, so C initially acts like a wire. So it acts like a wire if we take a look at Kirchhoff's voltage law around the circuit going this way. When that's first closed and the capacitor's acting like a wire, KVL is going to tell us that we're going to see minus VT first, and if we define our current direction as that way, we'll have minus VT plus IR plus the voltage across the capacitor. And all that must equal 0 as we come back to our starting point. But we also know that C equals Q over VC. And initially, well, VC therefore must equal Q over C. So if we write this a little bit differently, we've got minus VT plus IR plus VC I'm going to write as Q over C must equal 0. But at time t equals 0, the charge on our capacitor is 0. So at t equals 0, Q equals 0. If that's the case, that term is going to go to 0, and we get that minus VT equals IR, or VT equals IR. What's that mean? That's the same as if there was no capacitor in the circuit. Initially, you could pretend the capacitor's not there. It's just a wire. After a long, long time, however, now that's going to act like an open. In that case, as we do KVL around our circuit, we see minus VT plus IR plus VC equals 0. But if that's an open, then no current can flow. That means I must equal 0. Therefore, minus VT plus VC equals 0, or VT equals VC. The voltage across the capacitor is the same as what you have across your battery. There's no current flowing. So let's take a look at a couple graphs of what's going on. Let's start by looking at current flow. I'll make a graph of current versus time. Initially, we have a lot of current the moment that switch is closed. So we're going to start off here. But after a long, long time, current goes to 0. So we're going to have this approach 0. And we're going to say that at about 5 time constants, 5 tau, that's about 99% of the way to its final value. It's almost gotten to 0. It hasn't quite reached it yet. And what's that time constant tau? Tau is equal to the resistance of your circuit times the capacitance of your circuit. So that'll give you a time. Multiply that by 5, and by 5 times that, that's what we're talking about when we say a long, long, long time. Usually it's really not that long in terms of time we're used to. How about charge on our capacitor? If we look at charge versus time, initially we have no charge on our capacitor, and after a long, long time it's completely charged up. So we're going to have that go something like that, and after a long, long time, what's the charge on our capacitor? Well, if C equals Q over V, Q equals CV. So this is going to be C times V after a long, long time. But after a long, long time, the voltage across the capacitor is V terminal. So it's going to look like that. And again, you're 99% of the way there to your final value, right about the time you get to 5 tau, or 5 RC, whatever R and C happen to be for your circuit. And let's also look at the voltage across our capacitor. VC versus time. Initially, it acts like a wire, so the voltage across it must be 0. And after a long, long time, it works its way up until VC equals VT. So we'll have an asymptote here as well at VT. And again, this happens right around 5 tau, or 5 RC is where you get to 99% of that final value. How about when you want to discharge an RC circuit? Well, now we're going to pull that battery out of our circuit. We're going to have our resistor, R. We'll start off with a charged capacitor. We'll have our switch. So over here we have our capacitor, C, voltage across it, plus minus VC, and we'll define our current as going this way. And again, at t equals 0 is when we're going to close our switch. Well, if we close that switch at t equals 0, we know right away as we go around our circuit, Kirchhoff's voltage law, as we go around our circuit in this direction in a clockwise manner, I see positive VC minus IR, and I get back to where I start, must equal 0. Therefore, the voltage across our capacitor must equal IR. That looks like what we'd get if this was a battery there instead. So initially, our capacitor acts like a voltage source. But as time increases, as t gets bigger and bigger, as t approaches infinity, the charge on our capacitor is going to bleed off. The charge on our capacitor is going to start to approach 0. Therefore, the voltage across our capacitor is going to approach 0, and therefore, the current in our circuit is going to approach 0. So if we made a graph, some graphs of what we have going on now, let's start with current. I versus t. We start off with the full current, and over time we're going to bleed off that charge, that current, and approach 0. And guess how long that takes again? About 5 tau, till you get to 99% of the way to your final destination, or here in this case, 0. If we took a look at the charge on our capacitor versus time, well, initially it starts fully charged over here. And over time, that's going to bleed off again, so it's going to have the same basic shape as your current. And it's basically, it has 1% of the charge left after 5 tau, 99% of the way to its final destination. And finally, let's look at the voltage across our capacitor. VC versus time. And you can probably already guess the shape of the graph. We're going to start at the full voltage, which was VT when we were charging it, and over time we're going to get to about 5 tau again as we go close to 0, 5 RC. We're 99% of our way to that 0 level. So, charging and discharging capacitors. Really straightforward when we're looking at them at the steady state. When they're the circuit's first turned on, when they're uncharged, or when they're discharged or fully charged. The time varying element, what happens between 0 and 5 RC, we're going to save that till we have a little bit of calculus under our belts. So let's take a look at our first example here. What is the current through R2 here when the circuit is first connected, and what is the current through R2 a long time after it's been connected? Well, when it's first connected, in that case, C1 acts like a wire. So I'm going to draw the circuit as if C1 were a wire at that point to make it a little easier to analyze. In that case, we're going to have a 20-volt battery. We will have up here R1, 200 ohms. Then we're going to go to, we've got R2 here, which is 400 ohms. And we've also got in parallel with it, R3, 300 ohms. And that will complete our circuit. We'll draw it as if the capacitor wasn't even there because it acts like it's not there when it's first turned on. Well, the way I could figure this out is if we want to know the current through R2, well, that's going to be the current through that branch of the circuit right there. If that's I2, well, I equals V over R. That's going to be 20 volts over, well, what's our equivalent resistance going to be? The equivalent resistance of these two in parallel, 300 times 400 over 700, well, that's just going to be an equivalent resistance of about 171 ohms. So my total resistance, if I treat this as an equivalent resistor in parallel, is 200 plus 171, or 371, for a total current of 0.0539 amps. I2 then is going to be voltage 2 divided by R2. And our voltage 2, well, if we've got 0.0539 amps going through 200 volts, what we're going to have over here is, let's see, we've got 0.0539 amps through 200 volts. That's going to give us a voltage here of about 9.22 volts on this side. We've dropped 10.78. So that's 9.22 volts over R2, 400 ohms, to give us a current of about 0.0231 amps through that 400 ohm resistor. So there's the current through R2. How about after the circuit has been connected a long time? At that point, C1 is no longer acting like a wire, it's acting like an open. So let's go analyze that down in this bottom left region. When that acts like an open, that means this whole branch has no current flowing through it. We can ignore all of that. That becomes a nice simple series circuit. So the current flowing through R2 at that point is going to be the total current in the circuit, which is V over R, 20 volts over our equivalent resistance. We've got two in series now, 200 plus 400, or 600 ohms, for a current of about 0.0333 amps. So simplify the circuit and figure out what you need to using what we've already learned about circuit analysis. Let's do some more RC analysis, a little more practice. What's the current through R3 when the circuit is first connected, and what's the current through R2 a long time after it's been connected? Well, when it's first connected again, let's draw it that way. When it's first connected, we've got 10 volts. We have 100 ohms R1 up here. Now, when it's first connected, that's going to act like a wire, so we've got 200 ohms here. The capacitor acts as if it doesn't exist, it's a wire. And we've got in parallel with that another 200 ohms. And we want to know the current through R3. We'll call that I3. Well, what I would do right there is replace these parallel resistors with one equivalent resistance. That's going to be 100 ohms. So my total current is going to be, well, let's redraw that again. We've got 10 volts then from our power supply. We've got 100 ohms and 100 ohms, and a nice simple series circuit. Well, it should be pretty easy to see if that's 10 volts and we've got two resistors right between them here, we must have a voltage of 5 volts. And if we go back to this version, that means that we've got 5 volts here and 5 volts here, because anywhere on the wire must be the same. So the current flow through I3, which is V over R3, is going to be the drop across I3, 5 volts, over 200 ohms, which implies then that I3 equals 0.025 amps. How about a long time after R2 has been, what's the current through R2 a long time after the circuit's been connected? Well, let's take a look there. After it's been connected a long time, now this acts like an open. We can pretend all of that doesn't exist. We've got a very simple circuit now. 10 volts, 100 ohms, 200 ohms, and that's all there is to it there. And if this is R3, we want the current through R3. That's just going to be the total current because we have a series circuit. So I equals V over R, which is going to be 10 volts over our total resistance, 200 plus 100, since they're in series, or 300 ohms, for a total of 0.0333 amps. All right, let's try 2 more. What's the equivalent capacitance of the capacitor network shown right here? Well, we've got 1 in series, 2 in parallel, and 1 in series. So I'm going to redraw this with our 5 microfarad capacitor. Our 2 capacitors in parallel are very easy to calculate their equivalent capacitance. We just add them. So 10 plus 10 microfarads will be 20 microfarads. And then we go to our 3rd capacitor in series, 5 microfarads. So that's an equivalent network there. So let's find out the equivalent capacitance of this network. 1 over the equivalent capacitance is going to be 1 over 5 times 10 to the minus 6, 5 microfarads, plus 1 over 20 times 10 to the minus 6, 20 microfarads, plus 1 over 5 times 10 to the minus 6 again. Or 1 over C equivalent is equal to 450,000. Therefore, C equivalent is equal to 1 over 450,000, or C equivalent equals 2.22 times 10 to the minus 6 farads, which is 2.22 microfarads. All right, one last problem to try here. What is the equivalent capacitance of the capacitor network here shown below? And we've got 1 lead here and 1 lead here. This looks kind of complicated, so let's redraw it and see if we can't simplify it. These capacitors at 45-degree angles, they kind of trouble me. So if we redraw it, we could have, let's call this C1, C2, C3, and C4. We could redraw this as C1, and from C1 we go straight to C2, and then straight to C3, and then we come to the other end. Now we also have C4, which if I drew it this way, probably looks a lot simpler. All right, so what we really have here, we have 3 capacitors in series, all of those in parallel with 1. So let's replace these in series by one equivalent capacitance, an equivalent capacitance for C1, 2, and 3. To do that, I'm going to say 1 over C equivalent is 1 over C plus 1 over C plus 1 over C, or 1 over C equivalent is going to be 3 over C. Therefore, C equivalent must be C over 3. Now I could redraw this as one capacitor, C over 3, in parallel with our other capacitor. We still have C4, or just C. Capacitors in parallel, well, all you have to do is just add them to get their equivalent capacitance. So our total equivalent capacitance is going to be C over 3 plus C, or 4/3 C. All right, hopefully that gets you a good start on RC circuits. Thanks so much for your time. Make it a great day, everyone.